we are now going to demonstrate a shock tube facility which is installed in the gas dynamics laboratory of the mechanical engineering department of IIT Guwahati. So, this particular shock tube facility which we covered in the course modern compressible flow, and in the last module we have given all the theoretical details about the shock tube facility. So, in the laboratory we have installed a shock tube facility. It consists of a driver section and a driven section. So, as you see this driver section, this is a high pressure section for the shock tube, and they are connected by a pressure regulator, and subsequently it is connected to high pressure cylinders nitrogen and high pressure cylinder helium. But in one of the particular experiments, either we can connect it to high pressure nitrogen gas or high pressure helium gas. So, these two are the mostly used driver gases that are used for shock tube. Now, the most important part of this driver gas is that if we are going to use a higher molecular weight then of gas in the driver section, then it will lead to less shock wave velocity or Mach number. But however, when you are going to lower molecular weight gas which is helium, then we can the shock speed in the tube will be faster. So, now let us start with the driver sections. So, here in the driver sections there are two tubes of 1 meter length and they are connected through the flange. This stainless steel tube is width of 56 millimeter internal diameter and 12 mm thickness, and it is and what you see here is the diaphragm that separates the driver section to the driven section. What we can do now is that if you look at this particular tube, we have this driver section and driven sections, and this metallic diaphragm we are going to put it that will put it in this manner, so that the both driver section and driven section during the experiments can be distinctly separated. So, while performing the experiments, we will tell you how you are going to connect it. Now, when another important feature of this diaphragm is that this particular diaphragm is made out of aluminum material, and this is of 1 millimeter thickness. We can think of different thickness diaphragm if you want to increase higher shock speed. So, the diaphragm will rupture at its yield strength or at the pressure with respect to its yield strength, and when it ruptures, it has to rupture in a particular fashion. Then only we can say that a shock wave is generated. What does this mean? It means that while discussing about the shock tube theory, we have told that by pressurizing the driver tube, we are essentially increasing the compression waves, and these compression waves are generated, and at one particular time these compression waves has to merge and they have to come as a shock wave. Now, in this process of merging, if you do not use a particular fashion of this diaphragm, then this diaphragm can rupture abruptly. So, that is the reason we have made here a groove which is a V groove, and this V groove, as you can see, it has a pointed it is pointed at the center, and this section of this is a V shape, and this the diameter of this size of this circle would be something of similar value, which is the inner section of the shock tube. So, when it fits it, we try to see so that this rupture has to initiate from this center point, and when it ruptures here, it will rupture instantly at a particular pressure for which this L strength of diaphragm is defined. So, this is the basic philosophy, that the rupture pressure or instantaneous rupture of this diaphragm will generate the shock wave. Now, we will now move to one by one, we will now move to the driven section of the tube. So, you see that the driver section has two tubes each of 1 meter length, and driven section similarly it is connected from this end or the separation point of diaphragm, and there are 5 tubes connected in this sequence. Now, we are moving to the driven section of the tube. So, driven section of the tube is of similar length and material as used in the driver sections. So, as a thumb rule, when we are using two tubes of driver section of 1 meter length, similarly we have to use minimum of 5 meter of driven section length. This is mainly due to, as it is explained in the theory, that the introduction of shock wave also creates expansion waves that propagates back into the driver sections, and subsequently they reflect from the end flange and they interfere to our signal. So, for this reason, as a rule of thumb, we have been fixed that driven section tube will have 5 number of stainless tubes of same length, and they are also connected in the similar fashion using these planes. Now, let us come to the measurement part. So, there are, for the driver section and driven section, the measurement part consists of two things. One is, first thing we should know that at what pressure the diaphragm should rupture. That means, this particular aluminum diaphragm, when it is fixed in the junction point, at what pressure it should rupture. So, to do that, when you pressurize this through this gas cylinder, we side by side we monitor the pressure at which it ruptures using this pressure gauge. So, there is a pressure gauge which is connected to the driver section or high pressure section, and in the similar way we also connect this driven section using a vacuum pump, and so that by switching on this vacuum pump we can reduce the pressure, and side by side we can also monitor the pressure within this driven section of the tube using a simple manometer. So, this manometer will tell about the pressure in the driven section, and this pressure gauge will tell us that pressure in the driver sections. So, at the instant of rupture, this we can say that this pressure will keep on increasing, and once the rupture pressure of the diaphragm is reached, then again this value will come down. Now, this is how the driver section and driven section pressure measurement is undertaken while during the experiments. Now, we will move to the subsequent measurement part in the driven sections. So, just to tell you that at this junction of time, we say that this particular at this location the shock wave we are going to generate, this shock wave is going to propagate in the driven section, and this will keep on happening till this shock wave reaches in the end flange. Now, when this shock wave is generated at due to the instantaneous rupture, induced mass which is already in there in the driven section of the tube, it will also follow the shock wave. So, we have, as we have mentioned in the theory, that we have a shock wave which is moving towards the end flange of the driven section and followed by induced mass, and this and the driver section and driven section is separated by a diaphragm, and theoretically we call this as a contact surface. So, now let us move to the instrumentation side for the driven sections. So, we have seen that when the shock wave propagates in the driven sections, and across the shock wave there is a instantaneous rise in pressure of the induced mass. So, to measure that step response of this induced mass pressure, we have mounted two pressure transducers, and one is at this location which is 1885 millimeter from the end flange. Now, this for this driven section is terminated with an end flange at this location. Now, from this end flange location, the first pressure transducer that the shock wave sees is about at a location of 1885 millimeter from the end flange, and there is another pressure transducer which is located at a distance of about 500 millimeter from this first pressure transducer, and at this location is about 1035 millimeter from this end flange. So, if you see this, if you take our reference as the end flange, with respect to end flange, the second pressure transducer is 1335 millimeter and the first pressure transducer is 1885 millimeter. So, now let us see the sequence of events that happens. So, in the driven section, the shock wave first propagates towards the end flange, and followed by the shock wave there is induced mass which is at a elevated pressure, and this elevated pressure we are going to measure through these pressure transducers. Now, a typical pressure transducer, as I can show you, so this is a piezoelectric type pressure transducer. So, you can see this is very simple system, is a pressure transducer which has a sensing surface which is very flat. Now, when it is mounted like this, so we are going to see the static pressure, because it is mounted on the towards the inner surface of this tube, and when the flow sees this, the sensing surface responds to this flow, and since it is a piezoelectric type, there is a diaphragm that vibrates, and subsequently through these oscilloscopes which is shown here, we are going to tap the pressure jump across the shock wave. Now, the instrumentation part for this pressure transducer here is that, so this pressure transducer has to be connected to a power supply unit, because this sensor has to be powered by the power supply unit, and from there the output from that is going to take in the oscilloscope. So, this is how the pressure transducer instrumentation with respect to oscilloscope is concerned. We are going to take the final measurement of pressure jump across the shock wave using this oscilloscope. The other important part of this pressure transducer is that when the shock wave travels in the driven section, the first pressure transducer sees it first, so it will respond immediately, but by that time the second pressure transducer has not seen it, so it will not show any signal. So, when the first pressure transducer is triggered, after certain time the second pressure transducer gets triggered, because this and since we know from this oscilloscope signal, we can record that how much time does the induced mass takes to travel from first pressure transducer location to the second pressure transducer locations. So, in this process we know the time from this pressure signal, and we also know the distance between these pressure transducers. So, this distance and this time from this oscilloscope will give you the shock speed. So, in this way we can get the shock speed, and subsequently knowing the speed of sound we can calculate also the shock wave Mach number. And this is so the pressure transducer does the two purposes. One is that it records the time, which gives the shock Mach number. At the same time it also gives the pressure jump across the shock wave. Now, this is how the now we have said that the shock wave has now crossed the first pressure transducer, second pressure transducer, and we recorded the signal. Subsequently, with the shock wave will travel, and finally there is the end flange. That means this is the end portion of the shock tube, and this is the end flange at which it's a simple tube where it's actually it's a kind of a end portion of the tube for which the inner surface is flat and the shock wave is trying to reflect. Now, when we are looking at the reflected shock wave, means that already the induced mass motion has gained the pressure jump of the primary shocks. So, the reflected, when the shock wave gets reflected from the end flange, it sees the mass which is already at elevated pressure. So, when it is the reflected shock wave travels back or in the opposite direction of this shock tube, then the second pressure transducer sees the reflected shock pressure and subsequently it is seen by the first pressure transducer. Now, in this environment already the medium is pre-elevated due to the primary shock, and finally when you see the pressure jump in the oscilloscope, we can see that there will be another pressure jump in the oscilloscope. So, which says that the reflected pressure is much higher than the primary shock wave pressure. So, all these things we are now going to demonstrate by conducting a simple experiments, and these experiments will tell you that directly it will tell you how the pressure jump is recorded instantly in the oscilloscope. So, we are going to show now that how a diaphragm looks like before the rupture of before its rupture and after its rupture. So, what you see here is the first diaphragm, and for this first diaphragm, this diaphragm is connected between driver and driven sections at the beginning of the experiments. So, as you can see, there is a V groove, and after the rupture, if we are able to capture the shock wave, means that all the compression waves merge and the rupture is initiated at this center point, then the figure for this diaphragm after this rupture will be, the photograph of this rupture after the rupture can be seen in this fashion. So, it means that this is a flower like petals and it ruptures from the center point. All the 4 portions or 4 leaves have a unique and uniform ruptures, as you can see from this photograph. Now, if at all the rupture is not initiated by shock wave, then what you can see an erratic fashion of rupture locations. Some are like petals, some are like bent, So, as you can say that this rupture is not due to the shock wave, rather it can be only due to the compression waves. That means, in this situation we can be sure that it is not due to the shock wave, rather due to compression waves. This is the pressure transducer which is mounted in the driven section of the shock tube. This is the sensing surface which sees the flow, and this pressure transducer is a model of 113B22, and this is made out of PCB piezotronics, and this particular pressure transducer is located at the driven end of the shock tubes. Now, we will move on the instrumentation for this pressure transducer, and this instrumentation is mainly power supply cum signal conditioner and the oscilloscope for the data acquisitions. So, let us see that what are the instrumentation for the pressure transducer and how you are going to acquire the primary pressure jump, shocks pressure jump, and the secondary or reflected shocks pressure jump using these oscilloscopes. So, for that purpose I have shown you the PCB pressure transducer. The connecting wires from the PCB transducers, which is mounted from the driven section of the tube, is connected to a power supply unit which is also made by PCB piezotronics. This power supply unit has a unique features that it also supplies the power to the pressure transducer, as well as it does it also suppresses the unwanted signal, and we call this as a noise. So, we call this as a signal conditioner. So, side by side it also conditions the signal as per the requirement. And second thing, and for the data acquisition part, as you can see, this data acquisition part in the shock tube experiment is a very simple instrument which is the nothing but oscilloscope. So, basically the oscilloscope captures the voltage time data from the pressure transducers. So, and the main unique feature for this oscilloscope is that it is a echo-Goya model, and its sampling rate is about 200 megahertz or 2.5 gigasamples per seconds. So, that means we can take samples of 2.5 gigasamples per second data in these oscilloscopes. So, it means that the short duration timely events can be taken, all these data can be taken, and all those data are recorded in voltage and time format. So, in the oscilloscope, the x axis refers to the time axis and this y axis refers to the voltage axis, and in our experiment our y axis is nothing but the pressure transducers. So, as you see, there are two colors of reference line, because we have not started the experiments. So, these two colors refers to each of the pressure transducers. So, that means this shows that two pressure transducers are connected in this oscilloscope, and this is at the reference line. We have not started the experiments. Now, when we will do the experiments, we will see that the pressure jump, which is for the primary shock as well as for the reflected shock, will be shown as a jump in this reference line. So, now in the y axis, since we have a y axis scale which is it is kept as 50 millivolt per division, that means one division refers to 50 millivolts. So, depending on how many divisions there is a rise, and corresponding calibrated number of the pressure transducer as supplied by the company PCB, we can exactly map what pressure rise had caused that rise in the voltage signal. So, now we will demonstrate, we are going to demonstrate an experiment which is going to be seen in this oscilloscope. Now, we are going to demonstrate the shock tube experiments. So, before the start of the shock tube operation, which means that filling the driver section pressure and vacuum pressure, one needs to find out or one need to do the all types of circuitry arrangement as far as the pressure transducer is concerned and the reference line for the data acquisition system. In this case, we have these oscilloscopes. As you can see, there are both reference lines for the pressure transducer, green and the yellow, they are at the reference level. Now, one thing we are going to emphasize here is that when you conduct the experiments, we have to keep this oscilloscope in a auto mode. That means, we are allowing the scope to capture all the informations as set within this scope. So, for that we need to fix a trigger lines. So, trigger line means any voltage. So, trigger line means it is a kind of another voltage, so which we are going to set. So, this line we can set it, means that any value above this it should capture. So, currently as a first guess, one may show that in order to capture all the events that happens for the shock tube, I am setting a particular value in the voltage scales, and from our experience it goes that if you set a voltage scale of about 3940 millivolts, then all the informations can be captured. So, as you see that we have set the trigger line at these locations and these are the reference line. Now, I am switching on these instruments, which means if I said that the oscilloscope is waiting for the data to come for its recording. So, here which I am switching on. So, that means we are setting this oscilloscope to capture the data. So, in this process we are now going to pressurize the driver sections, and at particular instant the diaphragm is going to rupture. The entire sequence of events starts, and the pressure transducer is going to record its signal in the form of voltage and time in this oscilloscope. So, as you see that we have inserted a diaphragm at this interface location between driver section and driven sections, and this pressure of the driver section we are going to record in a pressure gauge. So, for this pressure gauge you can see there is a reference line which is almost 0, but however, this is the instrument bias error, there is a marginal minor error. However, we can put this as a reference line, which is seems that there is a almost the pressure, or what we say with respect to this value is 0. Now, we are going to pressurize in the driver section, and we will see that the pressure recording data from this pressure gauge, we can see how the pressure is going to build up in the driver section. So, here you see that pressure keeps on increasing, and this pressure is being recorded with respect to PSI, and pressure is now 129, 141, 50, 156, 165, 183, 200 psi, 218 psi, 235 psi. So, you can see that at 262 psi it ruptures, and finally after this rupture pressure value comes down, and this pressure is finally steady state pressure once both the driver section gas and driven gas they mix up from the ultimate pressure, which is at the end of the experiment in the tube, is 85. Since we have not exhausted the gas from this shock tube, the final steady state pressure now turns out to be around 83 psi. Now, if I remove this exhaust valve, you can see that this pressure comes down further. That means we are keeping this gas out of the shock tube, and finally we are bringing back this pressure level to this reference line. So, this is how the pressure gauge connected to the driver section of the shock tube records the rupture pressure of the diaphragm. So, as you see from the scope, instantaneously both the reference line shifts up. So, you see there are two signals which is captured in these oscilloscopes. The yellow one refers to the first pressure transducer, which is located at 1885 millimeter from this end flange, and the second pressure transducer is located 1335 millimeter from the end flange. That means, when the shock wave travels in the driven section of the tube, the first pressure transducer sees the flow information of the induced mass, and this jump, if you can see, it is instantaneous, it is like a step. So, this instantaneous jump refers to the primary shock generations. Now, the subsequent event subsequently till that point of time, you can see that green line which is in the pressure transducer 2 doesn't have see the shock wave. So, it is shown as the same reference line. Now, after that when the shock wave reaches to the location of the second pressure transducer, this also sees the primary shocks. So, both for a certain duration of time in the time scale, the entire value of the for both the transducer remains same. So, this particular jump refers to the pressure jump after the primary shock. Now, looking at the when you are coming to the second pressure transducer, as you see that the reflected pressure jump is shown in another step rise of the signals. So, here the reference point is little bit reversed, because the second pressure transducer sees the reflected shock first. So, that is what it sees, the reflected shock first, and this reflected shock keeps on rising, and at this particular time it means that the entire induced mass has further rise in the pressure. That means, after this particular time scale the entire flow events is over, and this means that it is the arrival of the contact surface followed by the driver gas. So, there is a sudden rise in the pressure as well as. A similar trend is also seen in the second pressure, that means in our reference it is the first pressure transducer. So, with respect to end flange, the first pressure transducer shows this after a certain time delay, and similar value of rise in the voltage signal is also observed. And here if you see that by the time the flow has already been contaminated due to the arrival of the contact surface, so you do not see any steady region, there is a continuous rise in the pressures. However, at this particular, if you look at this particular time scale, there is some kind of steadiness is seen, whereas in the first pressure transducer, in the reflected events, there is no steadiness is seen here. And as I mentioned in the beginning, that the arrival of the contact surface or other driver gases which are unwanted in our scenario, this shows that further rise in the pressures. But at the outset, what we are going to demonstrate in this event is that using the shock tube and using the pressure transducers, we are capturing the pressure jump across the primary shocks, which is seen as the first jump for the pressure transducer 1, and also similar nature of the pressure jump at is across the reflected shock. So, this for the first. So, both the pressure transducer shows significant rise in the pressure jump across the shock wave. Now, looking at the y axis time scale, one can map that how much division it corresponds to. So, looking at the number of voltage divisions, one can capture the pressure jump across the primary shock as well as reflected shock. So, this is all about the end of this demonstration of the shock tube, and as we have mentioned in the theory, more details we can see, more details can be found from the theory class. At the same time, at the outset, I can conclude this demonstration saying that a shock tube can be considered as a impulsive facility for generation of high speed slug of mass for a short duration time. And its main application, as you can see here, we have also attached a section which is used as a enclosure for to study the deformation behavior for the metals, and which is not part of this course. So, at the end I will conclude this, that shock tube is a simple laboratory one dimensional tube mainly intended for impulsive application measurements, and this main application includes deformation behavior of materials, calibration of thermal sensors under step and impulsive response. Then to some extent we can study the ignition delay of potential fuels. So, these are the few applications of this impulsive facility, and its utility is very vast as far as the high speed flow phenomena generation under impulsive domain is concerned. Thank you.